Lagrange multipliers. In this video we will be going over Lagrange multipliers. As I've promised in the last video, we will be going over this example right here, but then with more steps and in more detail. So first of all, one of the most important things is that you first of all know the definition, or that you have an ansatz. In this example, the ansatz is pretty easy because we will basically use that repeat this for z partial with respect to z, and this is equal to 0. So now we basically already have like a system, or we have a system of equation, but this isn't enough to solve this problem, because with this one right here we don't have the constraint itself. Like the maximum is something like probably, I don't know, it's something like x is equal to 2 and y is equal to 0, and you can just use any z because z isn't represented in our f of x. But now we have to somehow use our constraint problem, and this is where we also use our g of x, because we now have differentiated our f. We will now repeat this for our g. So we have partial g partial x, which is equal to 2x. We have our partial g partial y, which is equal to 2y. And we have our partial g partial z, which is equal to 2z. If we go back on the top, this is our ansatz. We have to differentiate f, we have to differentiate g, but we also need to multiply g with our lambda itself. So now we can write our completed system of equations. So if we write everything down, we get the 2 minus 2x plus 4 plus 2x lambda is equal to 0. We have 2y plus 2y lambda is equal to 0, and 2z lambda is equal to 0. And we also know that our x squared plus y squared plus z squared minus 1 needs to be less or equal than 0. Okay. If you're well known in linear algebra, you can probably write this as a matrix and solve it that way. We will do it just by hand. We will start with our equation 1 right here. You'll write it down again right here. We have minus 2x plus 4 minus 2x lambda. And if we rewrite this in terms of x, we have that x is equal to 2 divided by 1 plus lambda. If you don't know how you get to this term, we can just calculate. We have minus 2x minus 2x lambda is equal to minus 4. We see this 2x, we can just take the x out, so we have minus 2 minus 2 lambda is equal to minus 4, which implies that x is equal to minus 4 divided by minus 2 minus 2 lambda. And if we take out the 2, we just get that we have 2, so we can just take the minus 2 out, so we have 2 divided by 1 plus lambda. This only holds if and only if lambda is not equal to 0. We can safely assume that lambda is equal to 0, but if it turns out that lambda is indeed 0, we will have to go back and change everything. But for now, we just assume that lambda is not equal to 0, and we will see what happens. Now we will go on with the second equation, our 2y plus 2y lambda, and we can just write it down here. So we have our 2y plus 2y lambda is equal to 0. We take the 2y out, so we have 1 plus lambda is equal to 0. Now, this equation right here only has two possible solutions. Either y is equal to 0, or that lambda is equal to minus 1. But, I did a mistake right here. This should not be 0, this should be minus 1. Or lambda needs to be minus 1. But in the equation 1, we just assumed that lambda is not equal to minus 1. So we will just go on and say, okay, y is equal to 0. Now we can go to the second equation. We have 2z lambda is equal to 0. And this implies that either z is equal to 0 or lambda is equal to 0. But if lambda would be 0, then we would have y equal to 0 and that x is equal to z, and this is not part of u. Hence, lambda cannot be 0, which implies that we have z equal to 0. And so we know that z is equal to 0, we know that y is equal to 0, and we have our last equation right here, our y squared plus z squared plus x squared minus 1 is less or equal to 0. So if we plug everything in, we have our x squared plus, we know that y is 0, so we have 0, plus our z squared, but z is 0, so we have 0, minus 1 needs to be less or equal to 0. For now, we will just say, okay, we want the maximum and the minimum, so we will just say they need to equal 0. We can just do that. So x squared needs to be 1. And this is true if x is equal to plus or minus 1. And this is our solution, our P max is 1, 0, 0, and P min is equal to minus 1, 0, 0. Those are our points of maximum and minimum in the ball U. You could calculate lambda, but we don't need to calculate it. And this is how you use Lagrange multipliers. I hope you enjoyed the video, and don't forget to like and subscribe so you don't miss any videos, and see you next time. Goodbye.